Hello, yeah. So, hi everyone, and welcome to another session of the Bangalore Theory Seminars. Today we have Akash Sengupta with us, who will give a talk on rank bounds and polynomial identity testing. Akash is an assistant professor in the CS department at Rutgers University. He obtained his PhD in 2019 in mathematics under the supervision of Janos Kolar from the Princeton University. He was a JF Rit assistant professor at Columbia University and following that, a postdoctoral fellow at the University of Waterloo before joining Rutgers. His research interests lie in mathematics and theoretical CS, particularly in algebraic geometry, computational complexity theory, coding theory, combinatorics, and number theory. Over to you.
Okay, thank you very much for the introduction, and thanks for the opportunity to speak here. Can people hear me online and here? Okay. Also, wait, is there a clicker? Is this a thing? Or
There's this one, black color.
black color? So I can just use my computer. Right? This is fine. Okay. Yeah, no worries. Yeah. Okay. All right. Great. And one question, like, how long is the talk? Okay. 1 hour. Okay, that's good. That's what I prepared. It's good. Okay, cool. So I'll talk about rank bounds in polynomial identity testing, and this is joint work with Avivav Garg and Rafael Oliveira, and they're both at U Waterloo. And like small advertisement, Avi is graduating, so if he applies for jobs, maybe if you want to hire him. But okay, so yeah, so the main topic is polynomial identity testing, and this thing kind of is connected to three sort of areas: theoretical computer science, algebraic geometry, and combinatorics. And the main object, which is common to all of them from the perspective of polynomial identity testing, is polynomials. So, and the field is usually like C, reals, or finite fields. Although for this talk, we'll mostly focus on characteristic zero fields. And so the polynomials will be the central object that we will work with. And so if we look at these three areas, sort of, in TCS, we have algebraic complexity theory, and we have algebraic geometry and combinatorics. So if I think of this like three different islands, and this polynomial identity testing problem is a problem that we find in the algebraic complexity island. And then when we try to solve it, it turns out that we get to go to the other islands. Okay? So what are the other things? Algebraic geometry studies the solutions to polynomial system of equations, essentially, and their geometry in particular. And algebraic complexity theory is concerned with efficient computation of polynomials. And all these three things, like there are many connections, but for this talk, they're basically connected via combinatorics. Okay. So we'll see. So the way we are going to do this is like a tour. So first we will look at the island of algebraic complexity theory, sort of review. Many people probably already know all of that, but we're just going to review and sort of see what it looks like, and then look at our problem of polynomial identity testing. And then we will see that when we try to do polynomial identity testing, we are naturally led to some combinatorial problems. So then we go to this island. And then we're trying to solve the combinatorics problems, then we realize that we actually need some tools from the third island, which is algebraic geometry. So we'll go there and then we use that to solve the combinatorics problem. And once we solve the combinatorics problem, it solves the PIT problem. Okay, so that's the flow chart. And yeah, so these are the things we're going to talk about. Okay, and at any point, if you have any questions, just stop me, ask. So let's talk about algebraic complexity theory. So essentially the idea is how efficiently can we do computations. That's what complexity theory thinks about. And from a practical point of view also, like many practical operations like matrix multiplication, discrete Fourier transform, they all are polynomial functions of input variables. So basically I'm trying to make a point why our computation of polynomials, why is this an interesting thing? Is, for example, if I take matrix multiplication, the output is a polynomial function of the input variables, right? And so the question is, how efficiently can we compute polynomials? Right? And algebraic complexity theory studies computation of polynomials using algebraic models of computation. And what is this model? So that will be kind of used for posing a PIT problem, is this arithmetic circuit. So I'm not writing down the actual definition, but you can sort of see that an arithmetic circuit is going to be a directed acyclic graph. And on the first layer, sort of, we're going to have a bunch of variables and scalars. And then all the other nodes, they will either be addition or multiplication. And the circuit will basically do these operations and output a polynomial. So for example, here it multiplies x1, x2 and adds x2 and 1, and then finally multiplies them, we get this polynomial. So that these circuits compute polynomials, and usually we fix a field and we have n number of variables, let's say. Okay. So, and now given any polynomial, we can always write down a circuit that computes it. Usually the kind of questions we are interested in, what is the smallest circuit that can compute a polynomial? And the size of a circuit is measured by the total number of edges. We can also think like, take the number of edges, number of vertices, add all of them, and which also includes number of variables. So it's like a sum of all of those parameters. Okay, that's the size. And we want the smallest size circuit usually to compute a polynomial. And this is the landscape of the algebraic complexity theory. It's like there are so many polynomials. There are some random polynomials and exponential degree, which are kind of hard and out of control. But then there is this class VP, which is all the polynomials which have small size circuits or efficient circuits. And the class VNP is all the polynomials whom basically we care about them, but we don't know if we have efficient circuits or not, right? And one particular polynomial of interest is the permanent, and the central question is like, okay, is permanent really hard from the perspective of computing with these circuits? And the main problem here is are these two classes actually the same? And if you know the P versus NP, then it's an algebraic analog of P versus NP. So that's the central problem kind of in this area. Okay, questions? V stands for, I think, Valiant, who defined these things. Yeah. Okay, question. All right. Okay, so let's talk about polynomial identity testing. So what is our problem? So we are going to have an arithmetic circuit which computes a polynomial. And what we want to figure out is whether the output polynomial is identically 0 or not. Okay, so that's the question. An example is, like the previous example, it spit out a polynomial. Our one circuit might spit out this polynomial, but you will notice this is actually the 0 polynomial, right? Okay. So we want to test whether this is happening or not. So to make it more precise, like what can we do when we are testing? So let's do a black box model, which means that we just have input-output query access to our polynomial. Right? So the circuit is there, and if I give it an input, it will give me the output, and I need to figure out whether it's the 0 polynomial or not. And we want to do this in deterministic way and in polynomial time, essentially polynomial in size of C, many operations. Okay, so the size of C is the parameter, main parameter, and then we want to do polynomial in many operations and figure out deterministically whether a polynomial was 0 or not. Okay. So that's the main problem. Okay, cool. Questions about this? So why is this problem interesting before we talk about that? So, if we have efficient PIT algorithm, this does tend to say something about the VP versus VNP problem. I am lying a little bit here. This Cabanes in Pagliaso KI paper does not say exactly this, but in spirit, I mean, maybe at someday we can prove this, or like there is somewhat of this, a statement like this, that if I have efficient PIT algorithms, I can explicitly construct hard polynomials, and that if I am able to do that, then that will solve VP versus VN. Okay, so from a theoretical perspective, if I had a deterministic polytime PIT algorithm for general circuits, I should be able to essentially construct hard polynomials. Okay. And from the practical perspective, many different problems usually reduce to PIT. So, for example, the famous primality testing of Agarwal-Saxena, the polynomial time algorithm for testing whether an integer is prime or not, they actually use a polynomial identity testing for a specific polynomial. You come up with a polynomial, and then whether it's 0 or not, you use that algorithm. And similarly, perfect matching, like I can take a graph, and then there's this theorem of Tuft that you can write down a matrix, symbolic matrix out of your graph, and look at the determinant of that symbolic matrix. It's going to be a polynomial. That determinant polynomial is identically 0 if and only if my graph doesn't have a perfect matching. So many problems reduce to testing whether a polynomial is 0 or not. And if I have efficient algorithms for PIT, I will have efficient algorithms for many natural problems. Okay, so that's also another reason we can be interested in PIT. Okay, questions? Okay, good. So let's talk about algorithms for PIT. There are many different cases and many different algorithms, but some things which are relevant to the talk I'm going to focus on. First of all, there are very efficient randomized algorithms. You know, if a polynomial was non-zero, if I plug in a random input, it should give me a non-zero output. Right? So that's what you can do, and it gives us a very efficient algorithm. That's the Schwarz-Zippel. And more concretely, this is based on the Schwarz-Zippel lemma. So let's understand this or like review this a little bit. Is if I have a polynomial p in n number of variables, which is non-zero of degree d, right? And if I take a subset of my base field, and I take the n-fold product of the sets, which is like a hypercube, right? And I look at, so ZP is my notation for the zero set of P. So I look at how many points inside S to the n does P vanish. And there is an upper bound, this has to be at most D times size of S to the power n minus 1. And this is just a generalization of the elementary fact that a degree D univariate polynomial, if it is non-zero, it has at most D roots. Right? So for like n equal to 1, we will recover that statement. Okay, cool. So that's the Schwarz-Zippel. It says that basically in a hypercube, there cannot be too many zeros of a non-zero polynomial. And in probabilistic terms, if I pick a random input from S to the n, what is the probability that P will evaluate to 0? It's less or equal to D over size of S. So as soon as my field size is at least, let's say, twice D, then I can choose points and take S to the n and take a random input, evaluate, and with some probability, with some error, I'm going to randomizely say that whether my polynomial was 0 or not. Okay, so that's the randomized algorithm. This is very efficient. Okay. But we are interested in deterministic algorithms because, you know, at least from the, like in the previous thing, as soon as I have like, if these algorithms are deterministic, these will all be deterministic. And to do that application also, we need an actual deterministic algorithm. So that's why we're interested in de-randomizing the PIT problem. Okay, cool. So what about efficient deterministic algorithms? So far, there is no deterministic polytime algorithm for general circuits. Like if I just give you a circuit of size S, can you do in poly S time identity testing? We don't know. Okay. Okay, but what if we just try a little bit? Let's think of the Schwarz-Zippel type argument. Okay. I mean, in the Schwarz-Zippel lemma, I didn't need to say, like, I didn't need to have this probabilistic statement. Like, this is a statement works over any field. So even if K was complex numbers and I just had a polynomial, I could try to pick a bunch of points and look at how many places it vanishes. But then the problem is I need to plug in at least these number of points to see that whether my polynomial was 0 or not. Right? But this is exponentially many because you see n is appearing in the exponent there. Okay, so that's not good because we need to evaluate at exponentially many points. So that's not polytime. So that's not good. But what if, so this is the first idea here, is like what if P, okay, P was an n-variate polynomial, but what if secretly P just depended on R number of linear forms, right? What if I could do a change of coordinates? After that, P just depended on R number of forms. And what if this R is really small, right? So then I'm really working with R variable polynomial ring, and I could do with bs to the power r minus 1. And if r turns out to be constant, then basically we don't have to do much, right? So that's one idea. And so this kind of thing, that r is small and p is in the algebra generated by z1 to zr. So this kind of thing we'll call a small subalgebra. Okay, so and a polynomial like a subalgebra generated by, we look at this polynomial ring and then look at the subring generated by these things. That's the subalgebra, and because r is small, we're calling it a small subalgebra. Okay. Question. So basically, the idea is going to be: can we put our polynomial in a small subalgebra? Then maybe we can do PIT efficiently. Okay. Question. Yeah. So I kept it a little bit vague, but we're going to do a bunch of examples in the next slide. And yeah, the first case would be to think they are just linear forms. So up to change of coordinates, they are actually variables. But as soon as we go to depth 4 circuits, we need to work with them being actual higher degree polynomials. Okay, cool. So some examples where this happens, that P is secretly depending on smaller number of stuff, right? So let's look at this polynomial P. It's in 2R variables, right? But if I set Z1 equal to X1 plus X2, Z2 equal to X3 plus X4, and so on, I have P is basically Z1 square plus Z2 square dot 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 ZR square. So it just depends on Z1 to ZR, and R is N over 2. Okay. And sometimes this R can be really small, it can be constant. For example, let's look at P, which is L1 square plus L2 square, and so on. And these LIs, they are like trivariate things. Okay. And they depend on 3 linear forms, and each of those linear forms are in a polynomial. So if I do substitution, P is an n-variate polynomial, but essentially it depends only on 3 linear forms after change of coordinates. So it's really P really depends on 3 variables. So it's in a small subalgebra generated by 3 linear forms: Z1, Z2, Z3. Okay. Question? Yeah. So this R can be sometimes really small. It can be like a constant. It can be n over 2. Right? But the point is, like, polynomials in n variables might actually be completely governed by smaller number of variables. Okay, and that's what we can utilize to do PIT. Okay. All right. And yeah, and about that question, like sometimes we might have this kind of polynomial. So if you look at P, it's x1 squared or xn squared, and similarly for y, right? So P is this, depends on 2 n variables. But if I write q1 equal to the first quadratic inside and q2 is the second quadratic, then P is q1 squared plus q2 squared. So P is in the algebra generated by q1, q2. And if you look at q1, q2 individually, they are in completely different variables. So they should be, first of all, they are algebraically independent. So they should behave like independent variables. So that's the philosophy. We will make this precise at the end of the talk. Okay? But this is the kind of stuff is like when we are not able to find constantly many linear forms, so that P is in the algebra, maybe we go for constantly many higher degree forms so that P is in the algebra, and somehow utilize that. And what's the advantage? If P is in such a small subalgebra, like you see here, the transcendence degree of the generators Q1, Q2 is transcendence degree over the field is 2. They're both algebraically independent, and that's the transcendence degree. So the idea would be, okay, we have the polynomial computed by a circuit, maybe try to find a small subalgebra generated by higher degree forms, but those forms have bounded transcendence degree. We can control the transcendence degree. So then we are really dealing with a smaller polynomial. Okay, that's the idea. Okay. Question? Yeah. Question? No question? Okay. Sorry. All right. So just to recap, our first idea is, what if P is in a small subalgebra? That should help us. Okay, so when can we actually get these polynomials to be in small subalgebras, right? So doing PIT for general class of circuits is difficult. We don't know. So so people have been looking at low depth circuits where this kind of phenomenon appears, that we can actually show that they are in small subalgebras. Okay, so first we're going to focus on depth 3 circuits. So depth 3 and depth 4 are the interesting ones, and they sort of, well, they are almost enough to get us all the way for quasi-polynomials. So, okay, because of this result of Agarwal and Vinay, is that if you look at low depth circuits, that is almost good enough to study, like to get to general circuits. Why is that? If I had I'm going to show what it means to be depth 3 or depth 4, but just think of them as being low depth. Like the depth can be like the depth of that directed acyclic graph. So for low depth things, if I can have deterministic polytime PIT algorithm for unrestricted depth 3 or homogeneous depth 4 circuits, we can get quasi-polytime algorithm for general circuits. So we won't get polytime algorithm for general circuits, but it's not so bad because we still don't know this. And polytime PIT for low depth will give us quasi-polytime for general circuits. So it's quite good to study. We can be sort of content for the time being to look at these low depth circuits. Okay. Question? All right. So what do these low depth circuits look like? So first example is a sigma 3 pi sigma. It's the depth 3 circuit. So what does this notation mean? So the way I think of this is like the first sigma, and I put a 3 there, which means my polynomial will be expressed like this in the end, where I have 3 summands. And what will each of the summands look like? They will be a pi sigma, which means, first of all, they will be a product of a bunch of things. And each of those things will be a sum. And that is sum of variables times scalars. So that's why this sigma just means like linear forms, product of linear forms, and then sum of 3 sums of product of linear forms. So let's say our circuit is a sigma 3 pi sigma circuit, and that means the output polynomial has this expression for some linear forms ai, bj, ck. Okay. Can we do deterministic polytime algorithm for these kind of circuits? Okay, so that's the first question. All right. So here, we wanted to capture that this polynomial, maybe it's in a small subalgebra. So how do we capture that being in a small subalgebra? Well, we just look at these linear forms A1 up to AD, B1 up to BE, C1 up to CD, and take their span, right? And whatever the dimension of span is, that should be the number of variables P depends on. Okay, so the notion here is this rank. And if rank is small, then P is an algebra generated by Z1 to ZR. And Z1 to ZR can just be a basis of this AI, BI, BJ, CK. Okay, so what we're going to try to do is that show that we can bound the rank of a polynomial computed by sigma 3 pi sigma circuit. If it was 0, we should be able to bound the rank of these linear forms. Okay, question. So the key thing is like sigma 3 pi sigma looks like this, and the invariant to look at here is the rank. Okay, and the idea is that rank bound for identities implies deterministic polytime PIT. Okay, so imagine that I showed that take any sigma 3 pi sigma circuit which evaluates an identically 0 polynomial. Suppose I guarantee that the rank can be at most 5. That means any such polynomial is actually a 5-variable polynomial, and we can do polynomial entity testing efficiently. Okay, so that's the second idea. All right, and this was developed in a bunch of works. I'm sure I missed many people, so I apologize for that. I just put some names just to attribute something. So the first theorem is that a rank bound is that there is a function R, so that, and we can replace that 3 with k. You will just have k number of summands. Okay. So you take a sigma k pi sigma circuit, and there is some assumption of technical assumption, simple and minimal, which just means that it's not a redundant circuit. Okay? So suppose a sigma k pi sigma circuit was computing the zero polynomial, then this theorem tells us its rank had to be bounded by R of k. And R of k just depends on k. It is independent of the number of variables. I could have a circuit involving million variables, but in the end, the rank is bounded by R of k, if k is fixed. Okay, so that's the rank bound theorem. And the other ingredient you need to do PIT is the variable reduction. Once you have this kind of result, that you can bound the ranks of identities. Identities meaning circuits which are computing identically zero polynomials. So once you have those rank bounds, you can get a deterministic polytime PIT. Okay, you can generate small, like efficient hitting sets for that. Okay, question? So for this talk, what is the new stuff? Okay? So we're going to focus on depth 4 circuits, and we're going to look at the analogs of these two things. Luckily, for depth 4 circuits, the variable reduction stuff is already done before, so we will just use it, and we'll see, like, what ideas we need to get rank bounds on depth 4 circuits, and there these algebras will have higher degree generators. Okay, question? Okay, so 2 questions we should ask is, where do these rank bounds come from? And number 2, rank bounds and PIT for depth 4 circuits. Okay, so now we are going to the combinatorics island. We'll just explore what's happening in combinatorics, and then we'll see that that is actually useful to go back and solve PIT. Okay, so we're going to switch gears a little bit and look at a very old problem in combinatorics that turns out handy here. So in 1893, Sylvester asked this question: in the Euclidean plane R2, suppose I have a finite set of points, okay, which has this property that whenever I take the line joining 2 of my points, there is a third point from my set which is also on that line. So if you look at this picture, I take a line joining these 2. I should have had one more point from my set F there. Again, I draw another line. There should be one more point from my set. And it's a finite set. That's important. If it's infinite, I can go on forever. But then for a finite set, is it true that all points have to be actually collinear? Okay. And this was also independently asked by Erdős, and the answer is yes, they all have to be collinear. Okay. And in R2, the proof is there are many different interesting proofs which are generalizable, but there is a really simple proof on Wikipedia which a high school student can do. And so, yeah, so that's why I like this. This is really simple. So the conclusion is that they all have to be collinear. Okay, but the same thing works in higher dimensions. So suppose in R to the n, I had a finite set of vectors, right, or finite set of points, let's say, that the line joining any 2 contains a third from my set, then the linear span of them is at most 2-dimensional. So they all have to be on the same line. So the vector space span is 2-dimensional. Okay, so it works in higher dimensions. That's known as the Sylvester-Galai theorem. Okay. So, and instead of saying points and lines, we can also say vectors and span of vectors is equivalent. And it also works over complex numbers. So in fact, any characteristic zero field, you will have this kind of theorem that I have a finite set of pairwise linearly independent vectors. Okay, so that their span is actually 2-dimensional for each pair. So pairwise linearly independent vector such that whenever I take 2 distinct vectors from my set, there is a third one from my set in their span. Under this condition, the Sylvester-Galai theorem tells us that the span of F, the linear span, is at most 3-dimensional. So that's a rank bound. And the good thing to note here is that it didn't matter how large the ambient space was. It could be very large, like arbitrary number of variables of the polynomial ring. As long as I have these local dependencies, I get a global rank bound. Okay. So that's the combinatorics result. And there have been many generalizations and different proofs And yeah, I just listed a few. And the point here is that Kelly's proof actually depends on some work of Hirzebruch, which is like, algebraic geometry. It's really a deep algebraic geometry. It's if you don't like, yeah, it's hard to describe if we don't know algebraic geometry. But the good thing I like is that the other proofs, they are completely linear algebraic. So they're elementary, but that does not mean they're easy. The other elementary linear algebraic proofs are difficult, but they're still elementary. So that's why I like them. And they somehow work in more generality. So that's also one advantage. This algebraic geometry proof, it's not so easy to generalize to higher dimension, or like higher degree polynomials. But anyway, that's just some comments for this. Okay, question? VIs are higher degree polynomials, and the vector space is, let's say, polynomials of degree at most d in n variate. So that's a finite dimensional vector space. And yeah, that's how we will actually apply these terms. Okay, question?
This is for algebraically closed fields.
Yeah, so like if I had a bound over algebraically closed field, then I also get a bound over non-closed. So I would just go to the closure and get a bound. It won't be optimal, but the bounds will work. Yeah. But characteristic 0 is important. This totally fails in characteristic P. In characteristic P, in fact, like a finite field to the power n is a finite dimensional vector space, but it's also a finite set. So I could take all the points in Fp to the n, and there won't be any rank bound. Okay. Question. All right. For PID, there is another colored variant which is actually useful. So let's look at that. And yeah, like if the colors are hard to see, I would just think like first color, second color, third color. Or if you can see the colors, then like red, blue, and green. So let's say instead of just like the previous one, this time my finite set is given to me partitioned into 3 subsets: a red subset, a blue subset, and a green subset. And suppose I have this property: whenever I take a red and a blue vector, their span contains a green vector. And similarly for the other pair of colors, for all 3 combinations, this happens. Then again, there is a rank bound. The span can be at most 3-dimensional. So that's called the Edelstein-Kelly theorem. Question? So how should we think of all these theorems? So these Sylvester-Delaye-Edelstein configurations, Edelstein-Kelly configurations, they are finite set of geometric objects with local constraint or dependencies. And what turns out is that they end up being low dimensional. So there's a uniform global rank bound. And I say uniform because the dimension of span is bounded by a constant which is independent of the field, the number of variables, and size of F. Okay. And what's happening here is like a local to global phenomenon, that local dependencies give us a global constraint like rank bounds. Okay. And if we think of this, and that's like, this is the kind of perspective we're going to use, is that our geometric objects will be polynomials, maybe higher degree in some variables. And local dependencies will be some dependencies that come out of algebra looking at the identities. And we're going to show that they have rank bounds. Okay. So yeah, now let's see how can we use this to, why does this help for doing PIT? Right. So let's go back to our depth 3 circuit with this top fan in 3. So our polynomial looks like this. And remember what we want to do for the polynomial, for the identities which were evaluating 0 polynomial, we want to get a rank bound for them. Right? That was the second thing. If you have rank bound, you get PIT. So the goal here is to get rank bound. And the idea of the V and Shpilka is that we should really think of them as colored. So now if you think of them as being colored, what's something we can notice? If AI and BJ vanish at an input, then the product of the other linear forms should also vanish on that input. Right? In particular, one of the inputs should also vanish. Okay? So if you look at this, you can actually prove that CK has to be in the span of AIBJ. Okay, but let's do it in a more complicated way, which is generalizable. So what this statement means, if you forget the second part, AI and BJ vanish. That means C1 up to CD, their product vanishes. And algebraic geometry has this Hilbert-Snow-Salazar, which tells us that this product polynomial has to be in the radical of the ideal generated by AI and BJ. Okay. And what is this radical? This radical is just, yeah, I don't have something to write. I can just write. This thing is just, so if I have AI and BJ, this radical, this is the set of all polynomials, F, such that some power of F is expressible like this, maybe G times AI plus H times BG, but these are polynomials.
You just use that side.
Right here?
Yeah, that side is not.
Okay. So given two polynomials, let's say AI and BJ, what is the radical of AI BJ? This is the set of all polynomials F, so that F has a power which is expressible in the following way: G times AI plus H times BJ, where these two are polynomial coefficients. The polynomial in our ring x1 up to xn, and I started with all of this being in my polynomial. Okay, so it's a non-linear dependence. Like there are some polynomial coefficients, so that I can multiply and add and get a power of n. That's what it means to be in the radical. Okay, so and like one of the fundamental results in algebraic geometry is this Hilbert-Snow-Salazar, which essentially tells us this: whenever this happens, that whenever AI and BJ vanish, F, which is your product of C1 up to CD, vanishes, then F has to be in the radical. So some power of C1 up to CD is expressible in that manner. Okay, that's something to keep in mind. But then we can also notice that this AI and BJ are linear forms, so this is a prime ideal. And if just like if a prime number divides a product of numbers, it has to divide one of them. So one of these have to be in the ideal AI BJ. Moreover, because AI BJ CK are all linear forms, degree 1 homogeneous, so it actually has to be in the span of AI BJ. Okay, so we kind of took a long route, but we proved that CK has to be in the span. And now you notice that this is the Edelstein-Kelly condition. I could have done with the other pairs, DI and CK, some AJ will be in the span, so on. So the conclusion here is that if a circuit was computing the identically zero polynomial, these linear forms are an EK configuration. And by the Edelstein-Kelly theorem, we have a rank bound. So which means the rank of the circuit is bounded by 3. So we can get a deterministic polynomial.
Did they use the EK theorem?
No, I think they just noticed it. I apologize for the misattribution. Like there are a bunch of papers, like it was not in their paper that they get a deterministic polynomial algorithm. It came much after, like Kanin, Shvilka, and a lot of papers later. I don't know where exactly this is written, but do you know? Yeah.
Someone noticed this later.
Yeah. So yeah, people say that okay, this was somehow noticed there, but not actually used to do this. Yeah, that's it. Thank you. Okay. So okay, cool. Okay, good. So that's how this combinatorics helps us do PIT to get rank bounds. And now, if we want to do it, to answer the first question, where do these rank bounds come from? Now, what about depth 4 circuits? Let's try to play the same game. This time, A1, if I have a depth 4 circuit, let's say top fan in 3 and bottom fan in D, so this symbol, what this means is that the polynomial computed by this will have this particular form. Again, 3 summands, but this time, each of them, instead of being linear forms, they're homogeneous. Okay, this degree should not be there. Homogeneous polynomials of degree at most D. Okay, so we went from linear to higher degree. Okay, that's the change. Right. Now we do the same thing. If AI and BJ vanish, then the product of C1 up to CR vanishes. So again, use that Hilbert-Snow-Salazar, and it tells you that the product has to be in the radical. Okay. But now, because they're higher degree polynomials, we cannot get a span dependency anymore. Okay, this might not even be prime. I cannot even get to 1 ck, and even if I get to 1 ck, there's no guarantee it will be in the span. So we get a very non-linear, but still some algebraic dependence. And that's the kind of local dependence we end up with. And the goal is to use these local dependencies to get a global rank bound. Okay. And of course, this happens similarly for the other pairs. And so that's like the, where am I? Just one, just yes. Okay. So that gets us to the local dependencies, and we can define this higher degree polynomial version of Edelstein-Kelly configuration. So we have, again, a set of polynomials of homogeneous polynomials of degree, let's say irreducible, homogeneous, degree at most d. I should also say finite set, that's important. And it's partitioned into 3 subsets, so that it has 3 properties that, okay, pairwise they're linearly independent. And for all, whenever I pick a polynomial from R, I pick a polynomial from G. Okay, my colors are switched. This should be like blue. Okay, like whenever I pick just the thing we did here, like this property, whenever AI and BJ vanish, then the product of all of the third set vanishes. Right? So it's in the radical. Okay, so that's the definition of polynomial Edelstein-Kelly configurations. And the question is, can we get rank bounds for these? Any question about this definition? All right, cool. So the question is, are these non-linear Sylvester-Edelstein configurations always low dimensional? In applications, we get PIT out of this. Okay, and this was actually conjectured. Ankit Gupta and Beacon, Mithnan Saxena, they're different kind of conjectures, but they all tend to conjecture that these nonlinear things should have uniform rank bounds. And uniform meaning independent of the number of variables. Okay, and the rank bound, the notion of rank, depending on what you like, you can think of either of these: transcendence degree of all the polynomials involved, transcendence degree over the field, or the dimension of k-linear span. It turns out, I mean, they actually conjectured to bound only this, but we actually bound this. So you get this as a consequence. So right now, like because we already know this, we can just think any of these notions of rank. Okay. All right. Okay, so that's what we actually proved, and we did a bunch of stuff. And these are all the non-colored versions, where I didn't have partitioned into 3 subsets. So they are always low dimensional. We can bound the dimension of span. And the thing that I want to talk about here is that the colored ones also admit uniform rank bounds. Okay, I didn't define the non-colored one. You just think of one set with the same dependency. Okay, so what's the theorem? Is that, again, there is a function. If you remember the old theorem, there is a function R which bounds the rank of depth 3 identities with constant top standing. So similarly, there is a function R such that any Edelstein-Kelly configuration of homogeneous polynomials of degree at most d, we have the dimension of span bounded by R of d. So the bound depends only on the degree of the configuration. Okay, it's independent of in how many variables we had in the polynomial. Okay. Question. Okay, and that's the point, that it's independent of the field. So the field also doesn't matter, and but for PIT we usually fix the field, so that's okay. And yeah, n doesn't matter, and of course it shouldn't depend on the number of polynomials. So we get this. Yeah.
On earlier papers, the notion rank was span.
Yeah, span. Yeah.
Not the transcendence.
No, yeah.
It was always stronger.
Yeah. We always get the span, and I mean, they are kind of like, they're not far from each other because of the way we prove it. We actually prove that we can put them in a small subalgebra. But once you do that, you get that transcendence degree is bounded. You also get that dimension of span is bounded because I have a degree bound. Yeah. Yeah, we could have like stated the transcendence degree, but they both come from being in a small subalgebra. Okay. Other questions? Cool. So this is the combinatorial theorem, right? I had a bunch of polynomials, and then we have these local dependencies. I get a global dependency, independent of variables, but depending on the degree. So, and if we go back and apply this to identities, then any sigma 3 pi, sigma pi d circuit C is similar to that old theorem for linear form stuff. It's very simple and minimal. If it was computing the zero polynomial, its rank will be bounded by R of D. And the rank of C is just the rank of A1 up to AI, Bj, and Ck together. Right? So that's just this is from that other theorem. This is just by definition of rank. Okay. Question. All right. So what does this get us? So this is the theorem I just described. The non-linear decay configuration has been uniform rank bounds. So you get rank bounds for sigma 3 pi, sigma pi d, these depth 4 circuits with top fan in 3, bottom fan in D. And you get rank bounds, and out of those rank bounds, you get a deterministic polytime PIT. And this step, we just use variable reduction of Beacon, Whitman, and Saxena. That if you can bound the rank, they showed that you can get efficient hitting set, you get deterministic polytime PIT. So the whole thing is to bound the rank, and that's what we achieve. Okay. Question. Okay, cool. So in the last 10 minutes, I want to highlight what are the, like, I'm not going to do the proof, but I'm happy to talk about it if you have any questions. Like, what are some key algebraic geometry principles? Like, what are the tools from the algebraic geometry island that will be useful here to do this? Okay, so first thing is the Stillman uniformity principle. So yeah, let's think about this. So let's say I have a polynomial ring in n variables. Okay, and I had an ideal inside of that generated by polynomials f1 up to fn. Okay, so like in each polynomial ring, I can look at some ideas, and this complexity of I is kind of vague. Like, just think of, like, naively how complex the ideal can be. The complexity, if the number of variables is very large, the ideals tend to get more complex. Okay? So what does this mean? For example, what are measures of complexity? For example, the degree of an ideal, the transcendence degree of the number of forms, right? Because, you know, in a 2-variable polynomial ring, if I take 100 polynomials, their transcendence degree is at most 2. But in a 100-variable polynomial ring, I can have transcendence degree 100. So as the number of variables grows, the transcendence degree of f1 up to fn can grow in an unbounded way. So that's what it means, that like geometric, algebraic properties of the ideals, they become more complicated. They tend to grow in an unbounded way if I let the number of variables go to infinity. Okay, this is just something that happens. But what is Stillman's uniformity principle? It says that, well, if we are a little bit more careful, we can say something better. So Stillman basically conjectured this, that the complexity of I is uniformly bounded by a function of m and d. And the field doesn't matter, number of variables don't matter. Okay. And I just said, like, this is really vague, complexity of I, which just means that you pick one measure of complexity. You should be able to bound. For example, if I pick the degree of I, it's always bounded by d to the power m. Because degree of each polynomial, each generator is at most d, and I have m number of generators. So Bezout's theorem or something tells you, that kind of thing tells you degree is bounded by d to the m. So take any kind of algebraic geometric measure, or like some numbers that come out of the ideal. All such numbers, and the nice ones, the interesting ones, they will always be bounded by only m and d. And the reason this was growing in an unbounded way is because we were letting m and d become large. Okay? So if you look at the class of ideals in maybe infinite variable polynomial ring, but look at class of ideals which are generated by 5 polynomials, each of degree at most 10, you will have a uniform bound on their invariance. Okay? This was conjectured by Stillman, and this became a theorem in 2016 by Anand and Hofstede. And then there were a bunch of different proofs of this by different groups, but they all tend to say like this is the summary of all those results. Yeah, much more general. Yeah. Like Bezu is like all those are like corollary special cases of this. So this kind of unifies bunch of previous theorems and proves new stuff. Is like all those invariants of ideals, they're uniformly bounded in terms of degree and number of generators, independent of the field, independent of number of variables. Okay. And that was kind of, in particular, the number of, if you keep them fixed, then most algebraic geometric properties are bounded. And this was kind of the starting point is like, okay, we wanted to get some rank bounds independent of n. And this actually says something like that, independent of n. But the key thing is it depends on m, which is the number of polynomials. So we don't want that, right? So the idea is use the local dependencies to get rid of the m dependency. Then you end up with depending only on d, and that's our rank bound. Okay, and that's where most of the work goes. Okay, and well, I mean, and also like we cannot just go to their theorem and use the local dependency and get the rank bound. Like we have to build on that, prove different things, and but this is just the idea which I think is interesting and might be useful in other problems also. That's why I want to highlight this. And some key technical ideas which I think are also like kind of general, they appear everywhere in TCS and math, is kind of one thing I like is high rank polynomials tend to behave like variables. If you have seen like the Green-Tau theorem or these prime arithmetic progressions or like list decodability of Reed-Muller codes by Lovett. So they all are like this analytic rank versus partition rank. Like these, if you have seen any of these works, they tend to use the same philosophy. Is like high rank implies low bias for polynomials, and so the similar philosophy here is like given a polynomial, I can homogeneous. Let's say I can define its rank, and that notion of rank is going to be a generalization of rank of quadratic forms. So for a quadratic form, I can just do like a change of variables, and maybe I write it as, you know, L1 squared plus L2 squared or LR squared, and that R is the rank, where L1 to LR are linearly independent. So there is a similar notion for higher degree forms, which is similar to slice rank of tensors. But whatever the notion of rank is, the high rank polynomials tend to behave like variables. So we say a bunch of polynomials are collectively strong if we take their span, take any polynomial in their span, it's always high rank. Okay. So for example, the Q1 and Q2 we talked about earlier, their span, anything will be kind of high rank, because it will always look like constant times x1 squared or xn squared added plus other constant times y1 square, yn square. So rank is always at least n, and it goes up. Rank is always between n and 2n. Right? So it's pretty high. So they tend to behave like variables. That's what I meant. The Q1, Q2 together will be like variables because anything in their span is high rank quadratic form. Okay. All right. So that's the philosophy. And the key, like one technical useful thing, which might be useful in other places also, like I have seen this appear many places, this idea of regularization is like you start with something and it has a, right, like there is this structure, like I'm just going to talk about some philosophy for 30 seconds. And it's like, if I have something, then there is some part which is like random and some part which has more structure, right? And the stuff which is like random is like these high rank things. High rank things tend to be like random. So what you can always do in many problems naturally is like you start with some object and maybe you know how to prove things for random, and you're trying to prove something for arbitrary. So one idea is you start with your arbitrary thing, keep breaking it up into smaller parts. Some parts will be random and some will have some structure. If it has structure, you break it into further smaller structured parts. Eventually, you will get to all random pieces. And then you use your theorems for random to prove for arbitrary things. So that's the idea. And it's like this is regularization. Now you start with a bunch of polynomials. That's the objects I was talking about. And they might not be high rank, they might be algebraically dependent, they don't have to be like variables. But what we can always do is you can construct other set of polynomials G1 up to GS, which will be together high rank. So G1 up to GS will behave like variables because they will be collectively strong. And we didn't lose out our original F1 up to Fn, they are in the algebra of G1 up to GS. And the point is that I could have said G1 up to GS is just X1 up to Xn. That's no use because this S is too large. But the point is that this S can remain bounded by function of M and D. We don't need the number of variables. You can always bound in terms of M and D, break up into like this regularization process, you get a subalgebra. So that's one key idea. And what do we do with this? Just last slide is, okay, we construct small subalgebra containing all our forms in my EK configuration. And we have to use a lot of combinatorics and algebraic geometry to do this. And then we have a rank bound and a bound on transitivity. And the key is to get rid of dependency on M. If I just blindly did all of this, I would always end up depending on M. But inside, you have to use the combinatorics and algebraic geometry stuff to get rid of dependency on M. So that's how we get the rank bound. And I can explain more later. And open problems, of course, like we did it for 3. What if I have K? Think of K and D as constant. Can we get rank bound? Can we get PIT for depth 4? And maybe, I don't know. Yeah, this is a like more difficult question. PIT for general circuits. Okay, so I stop here. Thank you. Question.
How bad does the RT look like? This function.
Oh yeah, that's very bad. It's like a tower of exponentials. So D really needs to be thought of, like we need to hold it constant. Then we get like, otherwise it's like this technique is, I don't think it will be useful for depth 4 circuits without constant top bottom fan. Yeah. Yeah, the questions.
For the question again, and the speaker. Okay. Here's a small token of
Oh,
information.
thank you so much. Oh, wow. Okay, thank you. Yeah, I wore the same shirt twice. Like when I met you, maybe that's why. Yeah, thanks for the t-shirt. Yeah. Okay, so should I choose?